Welcome to our next installment of thermodynamics. Today we'll be talking about heat of formation. Before we get to heat of formation, I want to talk about just general thermodynamics. In front of you, we have 5 matches, one of which is lit. This is a combustion reaction in which the cellulose or CHOs of wood are converted into carbon dioxide and water with an extra oxygen being added. And it's exothermic. Energy is being produced. If we had 2 matches lit, it would be producing twice the energy. And 3 matches would be producing 3 times the amount of energy. And therefore, it is very important to understand how much we're talking about. When we want to discuss standardized amounts of energy, how much energy do you get when you burn glucose, when you burn octane, we need to specify the amount. And typically, we define the amount in chemistry as 1 mole. Off to our left, we have the ingredients for Nestle Toll House cookies. Those are so good. And it shows you the recipe. A recipe tells you how much goes in and what goes in, and it tells you what comes out, and we get 24 cookies from this. That would be a theoretical yield. Sometimes we eat the cookie dough and get less, but it's supposed to make 24 cookies. Just like when we have a reaction, we say how much energy is produced, we standardize it as saying per mole, but we can't always do that because in the recipe, everything isn't always 1. So here we have 24 cookies per 2 1/4 cups of flour, 2 1/4 cups of flour. Or you could say you get 24 cookies per 1 teaspoon of baking soda, or 1 teaspoon of salt, or per 1 stick of butter, or per 3/4 cup sugar, or 3 cups sugar per 1 teaspoon, 2 large eggs, etc. So you can't just say it takes 2 cups to make 24 cookies because it makes all these different amounts to make 24 cookies. Much like when we have balanced equation, if we have a delta H to the side of the delta to the equation, then the energy produced or absorbed is per balanced equation. And if you have a 2 coefficient in front of one and 3 in front of the other one, then it's per 2 moles of the first one and per 3 moles of the second one. I know that was kind of confusing, so let me show you an actual example. Here's the combustion of octane. Oct means you have 8 carbons, and this much energy is produced or released, because it's exothermic, 10,920 kilojoules, when 2 moles of octane are used. And when 2 moles of octane are used, 25 moles of oxygen are used. So it's also per 25 moles of oxygen. If we were talking about carbon dioxide, it would not be 25 anymore. It would be per 16 moles of CO2 being produced, because 2 equals 25, which equals 16, which equals 18. Tell that to your math teacher. So when 2 moles of octane are burned, you need 25 moles of oxygen used up, 16 moles of carbon dioxide, and 18 moles of oxygen are used. So when you have this type of situation, we have a balanced equation and delta H out to the side, it's referring to the balanced equation, not per 1 mole. And again, you would have to define per 1 mole of which one, because when 1 mole of octane is used, you're going to have 12.5 moles of oxygen, 8 moles of carbon dioxide produced, and 9 moles of water produced. Not sure if that helped, but hopefully. And we'll get back to heat of formation. Confused about heat of formation because they don't understand the definition and they don't understand how it's used. So I have a weird analogy like I usually teach in. The pictures given are of a hammer. And if I said, we're going to make a hammer, well, on the right side, the metallic head has already been forged, and they're shoving in the hardwood handle and then putting these tapered pieces of wood into the slit, and they're going to hammer it. Anyway, this is making a hammer. If I say we're going to use a hammer, I think everybody knows that means something completely different. So making a hammer or using a hammer is going to be very similar to what we refer to when we talk about heats of formation. Typically, we're going to use heats of formation to calculate a delta H for a balanced equation. And the delta H for the balanced equation will not be heat of formation. We're not solving for heat of formation. We're going to use heats of formation to solve for a different equation. Heat of formations are standardized numbers because it always requires a set amount of energy to make 1 mole of something. Below here is the definition. And delta HF means heat of formation. Heat of fusion, which is melting, is FUS. So delta HF is referring to heat of formation. The degree symbol right here, this is referring to standard reaction conditions, which would be 25 degrees Celsius and 100 kPa. That is standard reaction conditions, and that's what the degree symbol means. Delta H refers to a change in enthalpy, and in formation, we're going to form 1 mole of a compound. That is what it is, 1 mole. If it was 2 moles, it would be twice as much. So the product will be 1 mole of one thing, and the one thing is the compound. And what do you form it from? The basic elements in their standard states. In other words, elements in their standard reaction conditions. So what does it look like at normal pressure and 25 degrees Celsius? In other words, what does it look like if we had it right in front of us? We pretty much live in a standard reaction conditions. So let's see what it looks like when we have a heat of formation. Here we have two equations in which we are going to draw the equation for heat of formation. We are forming, in the first one, carbon dioxide. And if you form carbon dioxide from elemental forms, you have to use carbon. And carbon in the elemental form is a solid. And then we use oxygen. And oxygen in the elemental condition is going to be O2. That's how oxygen comes under normal conditions. And it would be a gas. Now, we need 1 carbon and we have 1 carbon. We need 2 oxygens, we have 2 oxygens. So this chemical reaction right here is a heat of formation reaction. And when you react 1 mole of carbon with 1 mole of oxygen to form 1 mole of carbon dioxide, it produces 393.5 kilojoules per 1 mole. If we had 2 moles, we would have this times 2. The next one is going to be heat of formation of a simple sugar. So we got C6H12O6, and it says 1,273 kilojoules are produced when you form how much again? 1 mole. We need 1 mole of this. So everything on the left has to balance out to 1 mole. So how many carbons do we need to have to form 1 mole of this? And we're going to need 6 carbons. Carbons are solid at room temperature. How many hydrogens? Well, we need 12 hydrogen atoms, except hydrogen comes as diatomic. So there's going to be 6 H2s, and they're gases. That is the way hydrogen exists in nature, is H2s. We need 12 atoms, so we need 6 molecules. And for oxygen, remember oxygen comes as O2. It's a gas at room temperature, and we'll need 3 of these. So 3 times 2 equals to 6. Now this is a balanced heat of formation reaction. When 6 moles of carbon and 6 moles of hydrogen and 3 moles of oxygen form 1 mole of glucose or some simple sugar under normal reaction conditions, this is the energy produced. Now this is what a heat of formation is. We need to talk about how we use heats of formation to solve for a delta H. Not a delta HF, but just a delta H for some chemical reaction that's not a heat of formation reaction. A couple of things. They will give you heats of formation to solve a problem, except they won't give you heat of formation for things like oxygen gas. And they won't give you heat of formation for things like carbon solid or for nitrogen gas. And the reason is, how much energy would it take, or what would the energy change be if you made oxygen gas from its elemental form? The answer is 0 because it is an elemental form. What about solid carbon from solid carbon? And the answer is it's going to be 0. And then nitrogen from nitrogen, and of course the delta H will be 0. So they won't give you delta H's for elemental forms, which is no problem. You just have to recognize that you don't need it. It will be a variable in a problem. And in algebra, if you know that one of the variables is 0, you can solve for it. But if you don't know what the variable is, it's unknown. So let's get to the actual equation. So here is the algebra equation we're going to use to calculate delta H for any kind of chemical reaction whatsoever. These equations are not heat of formation equations. We're going to be using heats of formation. So a minute ago, I was talking about how to make a hammer. Now I'm talking about how to use a hammer. Completely different. So before I was telling you how we come up with delta H of formation, and they use elemental forms. Now we're going to use those known values that we can look up in an algebra equation to figure out the delta H of some other chemical reaction. So the sigma P is the sum of all the products, and the sigma R, it would be the sum of all the reactants. And we're adding up the heats of formation for all the products, and then we're going to subtract that. We're going to subtract out, the heats of formation from the reactants. So it's last minus first. Everything in chemistry is last minus first, except for one thing, and we don't deal with that this year.